Welcome to Math 1324. This is section 4.2. We're going to look at some properties and some features of matrices. So here I have this rectangular array of numbers. It's arranged in rows. This is row 1, row 2, row 3. And you can terms of columns, column 1, column 2, column 3. So we say that the matrix has a particular size, and the size of this matrix is the number of rows by the number of columns. And so it would be 3 by 3. All right, in question 2. They're going to ask us if the matrix is square. Square would mean that it was the same size in terms of columns and rows. So it could be 2 by 2, 5 by 5, 3 by 3. Is it a column matrix? A column matrix can have many rows but just one column. And a row matrix is a matrix that has only one row and many columns. So for example, a column matrix might look like 2, 3, 4. So that's a column. And another example here is 1, 2, which is 2 rows and 1 column. This one would be 3 by 1. This one, when I have 1, 2, is 1 row and 2 columns. And that is a row matrix. Now, back to our story here. Question 2, this matrix has 2 rows and 3 columns, so it's 2 by 3. It's not square, it's not a column, and it's not a row, so it has no particular special type. In question 3, they want us to say, what are the elements on the principal diagonal? Well, the diagonal is, just as it sounds, the elements that go downward along the perfect diagonal line. And this particular matrix is 3 by 3, and so the diagonal is a perfect one. So I've got -4, -8, and 6. Now, they ask us in question 4 to identify A23 and A11. What does all that mean? Well, if you think of it in terms of I and J, where the I says the row that it's in and J is the column it's in. So let's see, if I look at this matrix here, and this matrix has 2 rows and 3 columns, what this matrix really looks like to me is it has a 1, 1, first row, first column, first row, second column, and the first row, third column. So that takes care of the first row, and that's why all of these are 1s. When I go to the second row, you see it's 2, 1, second row, first column, second row, second column, and finally the second row, third column. So when they ask us to find A23, it's the element that's sitting in this position in the second row, third column, and that's a -7. What about A11? Well, A11 is the very first position there, first row, first column, and that is a 4. So again, think of it in terms of I and J, where it gives us a particular row and a particular column where an element is inside. All right, in question 5, they want us to write down the coefficient matrix. Well, the coefficient matrix is I simply grab the coefficients sitting in the front here in this 2 equation, 2 unknown problem. And so 5, 7, 7 minus 5. So the sign would go with it. Now, if we include in this all of the information, we use something called an augmented matrix. It has the coefficient matrix in the beginning. The place where it has an equals, we have this vertical line, and we have the right hand side, which is 2 and 3. Okay, and so in question 6, they ask us to reverse this process. Okay, so they are giving us the augmented matrix, and they're asking us to put back in the variables. Okay, so the vertical line is where the equals is. So I see a 4 and a 3. This represents the first variable x1. This is the second x2. So 7x1 plus 2x2 equals 4. Similarly here, this is 1x1 plus 6x2 is 3. So 2 equations and 2 unknowns going from our augmented matrix back to the system of equations. In question 7, they're going to get us used to doing row operations. So here's our very first row operation, which says we can like to swap 2 rows. So whatever row 1 is, I'm now going to put it in row 2, and row 2 is going to become the new row 1. So you see, here was row 1, 1 minus 6 and 2, and when I swap them, it comes here into the second row. Don't change any signs, don't change any order, just swap the rows. And row 2 now becomes row 1. All right, in question 8, another row operation. We would like to take minus 4 times row 1 and then make that a new row 1 in our matrix. So let's see. All I have to do is take minus 4 and multiply it by each and every item in row 1. So minus 4 times 1 minus 4 minus 4 times minus 3 is a plus 12. Minus 4 times 2 is a minus 8. Notice row 2, nothing happened. This row operation only involved the particular row in question. Let's see. Question 9. What do they want us to do? They want us to take 8 times row 2. All right. Add it in to row 1. So I'm going to take 8 row 2, add row 1. Whatever that gives me, I'm going to write that as the new row 1. So let's see, where is 8 times row 2? So here's row 2. Multiply all the way across by 8. So I get 32 minus 48 minus 64. Row 1. Well, row 1 is 1 minus 3 and 2. And so now add them up. 32 and 1 is 33. Remember, it's going to become my new row 1. Minus 48, add a minus 3 is a minus 51. minus 64, add 2 is a minus 62. Now, the new row, row 1, which we just formed, is the only thing that's new. Notice in the process, row 2 remains the same. This operation of multiplying and adding does not change the original row 2. It's only making the new one that's on the right hand side. Alright, well, let's see. Question 10. They said, okay, what if we did this operation, we did something, and we ended up with our augmented matrix that looks like the following? But what does that mean? Well, let's see. This was x1, here's x2, there's an equals. So 1x1 plus 0x2 is minus 5. Well, 0 times anything is 0, so that's not there. And so this would say that the solution to this system is x1 is minus 5. And similarly from the second one here, 0x1 plus 1x2 is 2. And so x2 is 2. And so the system would have a unique solution of minus 5 and 2. What if we did the same operation here on question 11? What does that mean? Well, let's see. 1x1 plus 3x2 is 2. Oh, that makes sense. Okay. Now this would say 0x1 plus 0x2 is 2. But all of this stuff is 0. So that would lead us to the conclusion that 0 is 2. Well, that's not possible. That's just not true. And so what that says is the particular linear system has no solution. Now, how can you have something with no solution? Well, if we had two lines that were parallel, they would never intersect, and if they never intersect, there's no solution. So with two lines, they could be parallel. It could be something like we had back in question 10, where two lines intersected in a common point. And that's what we found back in question 10. So that concludes section 4.2, looking at the sizes of matrices and looking at various row operations and looking at the augmented matrix.